So, excellent. So now we get to the important part. For those of you who don't know me, I'm Gemma Davidson. I'm a research scientist in the Busick Center for Meteorite Studies. And it's my very great pleasure to introduce today's speaker. He's been my mentor as long as I've been in planetary science, pretty much. So I've worked with Larry since I was a grad student, and he was my postdoc advisor at Carnegie. So it's really great to have the opportunity to introduce him to you today. So if we could start with just a quick welcome to one of our newest professors. A round of applause. Yeah. So years ago when I was at Carnegie, I was really worried ASU were going to try and steal Larry away. But now that I'm at ASU, I'm really glad you stole him now. So it's great to have him here. So Larry is self-described interstellar dustbuster and heliochemist. So Larry, he straddles many different aspects of planetary science. He shows that you can do two very disparate things very, very well. So he studies pre-solar grains, and he also studies planetary scale bodies like Mercury. So Larry got his PhD in 1996 from Washington University. He worked with Bob Walker and Zinner there. They're two of the titans in the pioneering days of pre-solar grain research. And he's known very well for his work in pre-solar grains. He actually won the NEA Prize for his work on pre-solar grains as an early career scientist. It's the Meteoritical Society's award for early career scientists. And he's gone on to mentor a couple more NEA Prize winners for their work on pre-solar grains with him. And he's always been a really great mentor to me. Yeah. And so if you don't know Larry from his work on pre-solar grains and organic matter and crystalline materials, you might know him from his work on spacecraft missions. So while he was a staff scientist at Goddard Space Flight Center, Larry worked on the NEA mission. When he went back to Carnegie a few years later as a staff scientist, he worked on his pre-solar grain research, but also he was the deputy principal investigator of the Messenger Mercury mission. And now he's a co-I on the Bepi-Colombo Mercury mission. So he's not going to let Mercury go anytime soon. And in addition to the spacecraft missions, Larry's worked on a lot of samples that have been returned by missions. So he's worked on Genesis solar wind samples. He worked on Stardust cometary samples. And he's going to talk to us today about his work on Hayabusa 2 samples from asteroid Ryugu. So we're very excited to hear about that. So I will say that when Larry is not solving mysteries of the universe, he's also a jazz piano player. So if you need Larry, you need a piano player, you know where to find one. So with that, I'd like to thank Larry again. We're so glad to have you, and I'm looking forward to your talk.
Hey, can you hear me? Is this working? Good. Thank you so much for that introduction, Gemma. It is a great pleasure to be giving a seminar here. The last time I gave a seminar in this room I was speaking about Mercury, and it was about 8 years ago. So it's nice to be back, and this time not as a visitor, but as a member of the CC family. Very exciting to be here, and I'm looking forward to working with all of you. So yes, I'm going to talk about the Hayabusa 2 mission, but I'm going to work. Okay, already we have. There's a switch or something. The pointer is not working. I must have. Okay, thank you. All right, now it should work. Okay, I'm going to start way back at the beginning. In 1801, a Catholic priest in Palermo in Sicily named Giuseppe Piazzi discovered a new planet orbiting between Mars and Jupiter. He was looking for something else, but he found this slow-moving object and declared it a new planet. And he named it Sorella Ferdinandae after the Roman goddess of agriculture for Ceres, and after King Ferdinand III, of Sicily, his patron at the time. And the international astronomical community didn't really want it named after him, so it was soon shortened to just Ceres. And I do want to say that I think everybody should, every scientific paper should have a cover sheet with an illustration as cool as that. But the discovery of Ceres was followed quite shortly by the discovery of additional small bodies between Mars and Jupiter, Pallas, Juno, and Vesta. And already in 1802, Sir William Herschel named them asteroids, which means sort of star-like or star-shaped. And astronomers kept busy, and by the end of the 19th century, there were more than 100 known asteroids. And now, by today, there's more than 1 million known asteroids, largely because of automated surveys looking for ones that would be hazardous to us here on Earth. Most of those million are not named anything more than a number of the order they're found, but many asteroids are named. And in fact, I made this, quite a number of people here at CC have asteroids named in honor of them because of their work in planetary science. And this just is a snapshot of many of them. I'm sure I missed people, but this is all I could figure out today. And exactly where the asteroids are right now relative to the other planets. So you can see well represented. Why should we care about asteroids other than having them named after ourselves? And again, there's the whole issue, other than the issue of planetary defense and not wanting to all die, they're also very, very important scientifically for understanding our origins. The solar system formed from a rotating disk of gas and dust. That's an artist's rendition. We're now at the point where instrumentation like the ALMA radio array in Chile can actually take images of these things, so they really do exist. And during a few million-year process, disks turn into planets. And by the process of accretion, where dust grains grow into rocks, grow into planetesimals, and eventually grow into planets. And most of the stages of this process are not well understood at all. We're a long way from really understanding planet formation, but we've made huge strides and there's lots of very, very intelligent people having lots of creative ideas, and we're making progress. But what's really clear is that the asteroids themselves are the leftovers of this process. They're the planetary building blocks that did not get absorbed into larger planets. And so many of them really preserve basically a fossil record, a non-biological fossil record of the earliest stages of planet formation and the earliest stages of our solar system. They're also of great interest because many of them contain a lot of water and contain a lot of organic molecules, as we'll be discussing, and may have been really important contributors of these important prebiotic ingredients to the early Earth. They may be important to the origin of life. That's all I'm going to say about that. So, of course, asteroids are not visible to the naked eye. They were discovered by telescopes, and a lot of what we knew until recent decades was entirely from telescopic observations. One thing we know is that they come in different flavors, that there's for example, these are reflectance spectra, so it's showing basically how much sunlight is reflected off the surface as a function of wavelengths and divisible into the near infrared. And what you see is different types of asteroids show different spectra, reflecting different chemical compositions at their surfaces. And not only that, we see that these different compositions are distributed differently. So this is distance from the sun in astronomical units. The Earth is at 1, Jupiter's at 5. And you can see in the inner belt, you have E types and then S types. And then as you go farther out, you have C types and D types dominating. So you have these different compositions of asteroids. Well, in addition to telescopes, we can use spacecraft, of course. We're in the modern age of planetary exploration. The first spacecraft to visit an asteroid was Galileo, that stopped by an asteroid called Ida on its way to Jupiter 30 years ago. And it made the remarkable discovery that Ida had a moon, a little tiny asteroid moon named Dactyl. I love that picture. The first mission dedicated to exploring an asteroid was the Near-Earth Asteroid Rendezvous mission 20 years ago. And this passed by an asteroid called Matilda on its way to spending a year in orbit around Eros and studying that. Eros is an S-class asteroid that's in a near-Earth and Earth-crossing orbit. And then, of course, more recently, the Dawn mission spent a lot of time exploring Vesta and Ceres, the very first asteroid discovered, a minor planet. Dwarf planet, and returned a huge amount of data for both of those bodies. So, huge amount more about these asteroids. And finally, of course, the Psyche mission based here at ASU, led by Lindy Elkins-Canton, will hopefully launch next year to go explore the asteroid Psyche, maybe a giant chunk of metal out in the asteroid belt. That'll be cool. But we have another way of studying asteroids, which is the fact that fortuitously pieces of them come to us. So you have collisions in the asteroid belt that knocks rocks off, they fly around and gradually drift into the sun. And if Earth happens to be in the way on their way to the sun, they fall through the atmosphere. And we observe them. If they're too big, they kill dinosaurs. If they're really small, they make little pretty shooting stars and say, "Ooh." But a lot of them turn out to make it to the Earth, to the surface of the Earth, and they're extraordinarily important scientifically. N-System is a very famous fall from the late 1400s in France. It was the first modern observed fall in the scientific age in Europe, anyway. But even then, it was controversial in the scientific community whether meteorites were really rocks that fell from outer space or some atmospheric phenomenon or something. A few major falls occurred in the United States and in Europe in the early 1800s that changed all that and convinced the community that meteorites were real and important. We know now from fireball reconstruction, where you can document the trajectory of the fireball as the meteorite comes through the atmosphere. You can then sort of back calculate the trajectory and figure out what the orbit was of this rock before it hit the Earth. This has now been done for a number of asteroids. This is an old plot. There's a lot more meteorites than this now. And generally, they all originate in the asteroid belt. So we can tell from this kind of analysis the meteorites are originating in the asteroid belt. Now, we have a handful from the moon, handful from Mars, more from asteroids. So just like the asteroids, the meteorites come in different flavors. There's a huge diversity of different types of meteorites. The vast majority that fall on Earth are stony meteorites. Irons make up a very small fraction. These are often are in the popular imagination of what a meteorite is, a giant chunk of metal. But most meteorites are stony. A small number are even smaller number are mixtures of stony and iron, called stony irons. And of the stony ones, there's a few that are achondrites that are basically volcanic rocks from other planetary bodies. Most of the rest are chondrites, and these are primitive remnants of the protoplanetary disk. Most of them are ordinary chondrites, but today we're more interested in the carbonaceous chondrites that make up a few percent of the total meteorite falls. Carbonaceous chondrites are extremely important, partly because they have these interesting objects, or many of them do, these little white, weird-shaped things. There are many types of carbonaceous chondrites. They can range from a fraction of a millimeter up to centimeters in size, and they're little ceramic blobs, and they are the oldest things that have been measured in the solar system using radioactive chronology methods. And they define the age of the solar system. These are the first solids that formed from that disk at the very, very, very beginning. They mark time zero for planet formation in our solar system. They're very important in that regard. The meteorites have bulk compositions very similar to the sun. I will show that, which indicates that they representative of the disk. They are very heterogeneous mixtures. They're sort of, somebody's called them cosmic sediments. So it's sedimentary rocks from the disk. It's accumulated all these different things that were floating around and stuff. And they're probably an important source of organic carbon to the earth. So we'll come back to all of these, and that's why it's important, because what we find out is Ryugu is a carbonaceous chondrite. And that's the real question, is we know that meteorites come from asteroids. We know that asteroids come in different types. We know that meteorites come in different types. Can we make connections between meteorites and asteroids? If you pick up a meteorite on the Earth, you don't know what asteroid it came from, but maybe we can infer that. And if we can start applying the incredible amount of information we have from laboratory analysis of these rocks, especially with modern technology. We can learn so much of these on very, very small scales that we can connect that to specific asteroids or types of asteroids. It really helps connect what we would see in the lab to what we see in telescopes and spacecraft and what we model in computers to try and understand how the planet's formed. So there are a few cases where we can make these connections. For example, it's now very well established with the HED meteorites. These are the most common type of achondrites falling on the Earth. Almost certainly came from Vesta or from pieces of Vesta that have broken off Vesta in the past. And this is partly by comparison with reflecting spectra, and partly based on a whole lot of data that the Dawn mission acquired while it was in orbit around Vesta. Similarly, the NEAR mission, the Eros, showed pretty strong evidence that S-class asteroids, or at least Eros, is related to ordinary chondrites. And this was chemical data we got with that mission that showed, for example, that Eros had magnesium and aluminum and silicon abundances that overlapped with ordinary chondrites. But a fundamental question, it's also been assumed for years that carbonaceous chondrites are associated with with C asteroids. The C in asteroids is for carbonaceous asteroids, even though there was no real evidence in the past that these contain carbon. But it's been long thought that these are related, and that's a fundamental question. Are they? And the best way to find that out, to answer this question, go to a carbonaceous asteroid, pick up dirt and bring it back home. So there have been 3 asteroid sample return missions to date. The first one was launched almost 20 years ago. by the Japanese Space Agency JAXA, and that was Hayabusa, that went to an S-class near-Earth asteroid called Itokawa and reported its data a decade ago. And then I'm going to spend the rest of the talk talking about Hayabusa 2, which returned samples from a carbonaceous asteroid last year, or almost 2 years ago. And then simultaneously with Hayabusa 2, NASA has flown a mission called OSIRIS-REx, a New Frontiers mission, to an asteroid called Bennu, and those samples on their way back, they should be here in about exactly a year. So next year we'll have to talk about what was found in those meteorites, or in those samples. So the first mission again was Hayabusa. It went to this asteroid called Itokawa. One thing I want you to notice is Itokawa has these nice flat areas here, smooth areas, made it very easy for the spacecraft to touch down to try and get some grains. And I just love pictures of spacecraft shadows on other worlds. So anyway, this is one of the grains. The mission was successful. It had a lot of challenges. It both with the sampling mechanism didn't work correctly. The spacecraft lost most of its reaction wheels and almost didn't make it back to Earth. But it was plucky and made it back, and there were a couple thousand grains of asteroid dirt in the collector. And detailed chemical analysis showed absolutely that this asteroid is related to ordinary. This confirmed absolutely that S asteroids are related. So fast forward to Hayabusa 2. That was successful. JAXA said, yeah, let's do it again and do it better this time. And let's try a C-type asteroid. And they chose Ryugu. This is, of course, an image from the spacecraft. This is the time it was selected. It was just a fuzzy dot. But it was named while the spacecraft was en route to Ryugu, the asteroid was named that. And it's named for a Japanese fairy tale where it's essentially a sea monster's palace. And it's just kind of cool. And Ryugu itself it's an near-Earth asteroid. It crosses the orbit of both Mars and Earth. And near-Earth asteroids are prime candidates for sample return because it's not too hard to get to them and get back to Earth. It would be much harder to go all the way out to 3 astronomical units or something to come back. So this is the spacecraft itself. Has the normal solar panels for generating electricity, antennas to talk to Earth, various instruments. It's got this big thing I'll talk about later, which is the sampling horn for actually collecting samples, and a little sample return capsule for returning those samples to Earth. So the spacecraft is still going, only it no longer has this capsule because the capsule is now on Earth. It was launched in 2014, almost 8 years ago. And then followed Ryugu around the sun for a few years. And then in June of 2018, a little over 4 years ago, it encountered the asteroid. And these are just some approach shots as it got closer. And a week or so before encounter, it could resolve it well enough to tell, well, oh, it's diamond shaped. That's interesting. Because none of the other asteroids I showed you before, right, that spacecraft visited looked anything like it. That's super interesting. Cover its diamond. And got bigger and bigger. And of course, then we got there in late June. It is about half a mile across, 870 meters across, and it is completely covered with boulders. And this was a surprise. Remember, I showed you the thing in Itokawa. All the other asteroids that have been visited by spacecraft had areas that were very smooth, and it was assumed that all asteroids do, and that makes it easy to go down. It was immediately recognized this was going to be a challenge for sampling, because there's boulders that can flip off solar panels. You have to get very close to the planet. But in the end, it was successful. So to give a sense of scale for this is an aerial map of Arizona State University, and with some of the major buildings that house CC people. And that's the size of Ryugu. So Ryugu is CC sized. So before the samples came back, there were numerous instruments on the spacecraft. There also, I won't have time to talk about, there was a little tiny rover that the German Space Agency wrote that did some science from the surface. There were some other little rovers that were engineering tests. But I'm only going to highlight a couple of orbital science results. First of all, there was a thermal infrared instrument. And from the thermal properties, we could infer that the asteroid is extremely porous, 50, 60, 80%, something like that porosity. It's very clearly a rubble pile that formed from the disruption of some larger body that then reaccumulated into this porous clump of rocks. And because it was spinning, it formed this top shape. And there's a lot of modeling that shows this work. A high importance is the spectra that were measured. So the black curve is the spectrum, reflected spectrum in the near infrared measured by an instrument on Ryugu. The gray symbols here are ground-based spectrum of this asteroid. And the rest of these are various meteorites of different types. The first thing to notice is that Ryugu is really, really dark. That's 2% albedo. That's the darkest thing we've seen in the solar system in terms of an absolute albedo of the surface. We're not really sure why that is. The other thing is when you zoom in on here, you see there's a feature at 2.7 microns. That's a hydration feature from clay minerals, basically. And you can see it's quite deep in carbonaceous chondrites. We'll come back to that. It's quite shallow on Ryugu from the orbital data, and this led people to speculate that Ryugu might have. It looks very much like that. This red curve is a carbonaceous chondrite that was artificially heated in the laboratory and then measured, which dehydrated some of the water and made this feature shallow. And so there was some suggestion that maybe that's what some expectation that when we got to the sample stack, it would look like they had been hydrated but had been heated and dehydrated. So what about sampling? This is a movie they made beforehand to show how it worked. Basically, that sampler horn I showed you, goes down to the surface, and it shoots a tantalum bullet into the surface, which knocks material up into the collector, goes up and gets put into a collector in the sample return caps. You can see how that works. So anyway, there was a lot of discussion of where we could touch down. Finally decided on a site that didn't seem to have too many bad boulders, and this was a shadow shortly before taken by the spacecraft picture of the surface shortly before the first touchdown. This is a movie of the first touchdown. See if you can tell when the sampler horn impacts the surface. I think you'll be able to tell. I love this video. There we go. So you see huge amounts of material. So it shot the tantalum bullet into the surface. It knocked up huge amounts of material. There was a science paper earlier this year by Shogo Tachibana, led by him, that involved analysis of every single one of these fragments from these movie frames that gave us a lot of information about the physical properties of the surface. That's not the purpose of this talk. But this certainly gave us confidence that the mission successfully touched down. This was in February of 2019. A couple months later, there was another really cool thing called the Small Carry-On Impactor. This little spacecraft had everything. And basically, this was a little ball of copper with some explosives attached to it that was dropped by the spacecraft to make an artificial crater. So this is a video of it going down. Basically, the spacecraft dropped it and then ran around to the other side of the asteroid to make sure it didn't get hit by any problems from the explosion of the crater. And on its way back around, it dropped a little camera like this big into just on the side, 90 degrees on the side of the asteroid, just sitting there floating, so it could take pictures of the impact and send them back to the spacecraft. And that's what these are from, that little camera. And to my knowledge, this is the only images ever taken of this type of an impact crater actually forming on another planetary body. It's an artificial crater. This might be my favorite video in all of time. Everything about this is so cool. And it was obviously successful. This was before and after the impact. And you can see that, yes, there was a new crater, not terribly deep, not anything, but definitely there after the fact. And the team decided to go sample there for our second touchdown in the hope that we could get material that was might have been buried before the impact experiment. So the idea is the first collection was almost certain stuff from the very surface. The hope was that the second touchdown site would give us buried material that might have been shielded from the space environment. So the spacecraft explored Ryugu for a few more months and then left and came back to Earth. And the end of 2019, when it was approaching Earth, it had a number of engine burns. You see on this trajectory correction maneuver, for those who don't know. And that basically made sure that the spacecraft was in the right place at the right angle, so that when it let go of the sample return capsule, the capsule would float on its own to the exact right spot to land in Australia and be collected. And then a day or two later, it fired the engine again to make sure that the spacecraft itself didn't follow the capsule into Australia, and continued on going. And in fact, the spacecraft is now in an extended mission. It's headed to two more very interesting, very small asteroids. And it's doing measurements of the zodiacal light and trying to find transiting exoplanets and doing all kinds of science. This is a really cool mission. So keep your eyes peeled. In the next decade, we'll be finding out about Hayabusa 2 exploration, Hayabusa 2's exploration of these other bodies. But back to samples, which is the focus of this talk. Sample return was successful. There's a nice shot of the fireball it made as it came through the atmosphere. Next morning, helicopters very quickly found the parachute and the thing out in Australia, and a team of people came out and retrieved the capsule and brought it back to JAXA's facility outside Tokyo and put them in here. And this is this amazing apparatus they constructed in Japan to the giant vacuum system designed to open the sample chamber, pull out the samples, be able to analyze them by infrared spectroscopy, just physical property measurements without ever exposing them to air. And this was a very cool thing, and it was very successful. And after a few weeks, they managed to get all the samples out of the sample collector. And this is the sample of Ryugu that was brought back to Earth. Touchdown site 1, touchdown site 2. A bunch of little black rocks, very small. Total was 5.5 grams. That doesn't sound like a lot, but it's incredible what you can do with small amounts of material with modern instrumentation. So I'll be showing. The mission would have been considered a complete success if they'd returned 100 milligrams. So this was great, get this much material. So for the first 6 months after the sample return, beginning of last year, the curation team had the samples in this vacuum chamber. And they did a lot of basic characterization, started making the sample catalog, and started picking out samples to give to the analysis team, the initial analysis. And they did a lot of measurements on their own. They published their first results in late 2021, which was while the initial analysis science results that we found out were starting to be collected. So these are some infrared spectra taken of chamber A and chamber C grains. So I should have mentioned chamber A is what we refer to the first touchdown site, chamber C, the second. What you see is they found that the infrared spectrum was very similar for the two samples. This is, and very different from the orbital data. Remember, this is the black curves of the orbital data that had this very narrow or shallow feature. These samples show a much deeper sample, showing much more high level of hydration than we were expecting to see based on the remote sensing. There was no sign of any of these calcium aluminum-rich inclusions, the ceramic things I was talking about, no chondrules, which are a very common component of chondrites. Chondrites are named after the little millimeter size silicate balls. And in fact, basically, from this point of view, it was immediately said, this looks like CI chondrites. Well, what are CI chondrites? CI chondrites make up about 0.1% of known meteorites. These are very rare, but they're scientifically very important. This is just, this is sort of the total meteorite classification scheme. They're showing that carbonaceous chondrites are a subgroup of chondrites, and CIs are just one subgroup of C chondrites. But they're extremely important scientifically because of this graph here. This is the plot of the elemental abundances measured in CI chondrites versus the elemental abundances measured in the sun using spectroscopy and telescope. And with using silicon, an assumed amount of silicon to get them on the same scale. And there's a 1-to-1 correlation for almost every element in the periodic table over 10 orders of magnitude. So CI chondrites have solar composition, except for things that are, extremely volatile and don't go in rocks, like hydrogen, noble gases, hydrogen. So interestingly, if you look at this is by number, even though you don't think of hydrogen as an important rock-forming element, it's the second most abundant element by number in CI chondrites after oxygen. That's because they have a lot of hydration. These things are hydrated rocks. They have the phyllosilicate, clay minerals, carbonates, and so on. And this is a picture of the sample of orgues at the Natural History Museum in Paris. Orgues is one of the more famous CI chondrites. So after the initial curation team had a look, the preliminary examination by the initial analysis team began in the middle of 2021. And this was divided into an international team with more than 350 people, divided into 7 individual teams led by specific people. It's of interest that of these 7, 2 of these people, Hikaru Yabuda and Shogo Tachibana, who actually ran the entire team, are both alumni, postdoc alumni of CC. So CC hopefully had an imprint on this mission from the beginning. This is, I don't know if it's complete, but it was complete as of several months ago, list of the team. And again, I've highlighted CC or former CC people, members of the team. So there's a large number of people involved in this mission around the world, many of whom have spent time at Arizona State or are here now, like Mindy and Lisa and Rhonda. Personally, I was on the chemistry team and the insoluble organics team. And that's what I'm going to be talking about is the data from these. And their goals were to characterize the elemental and isotopic composition of the samples and the organic, macromolecular organic compositions of the samples to compare with meteorites and see what we can learn about the origin of the solar. These were the samples allocated to that entire initial analysis team, total of about 0.3 grams, so 5% or so, 5.5% of the return sample was allocated for the initial analysis. And in particular, for what I'm talking about, the chemistry team was allocated these 3 aggregates of samples and a couple of thin sections from these larger grains. And you can just see, it's not a high resolution image, but that's what it looks like. But a third of the total sample was given to the chemistry team because a lot of the key measurements required dissolving fair amounts of material to do high precision measurements of various isotopes. The chemistry team, the organic chemistry team, got much less material. We got material from these two aggregates. But in the end, the techniques we're using require such little material that 8 milligrams is more than sufficient to do a huge amount of science. I'll be talking about. So I'm going to jump right to the results. There was a paper appeared a couple months ago in Early View on Science, led by Yokoyama, but with, I don't know, 150, 200 co-authors or so, names you'll recognize on here, and reporting the first results of the chemistry team analysis. And the fundamental conclusion is, yes, Ryugu is a Ci chondrite. It's not a chondrite in the sense that it's not a meteorite, it didn't fall from space, but it's clearly very, very closely related to Ci chondrite meteorites. So I'm going to show some of these data why we think this. This is a backscattered electron image and then a mineral map based on X-ray mapping. And this looks, anyone who's ever looked at a Ci chondrite knows this is what it looks like. Made of this fine grain phyllosilicates, you have these sulfides and carbonates there. It's very typical Ci mineralogy, except that there is no observation of any sulfates, which are commonly seen, not as in high abundance, but are seen in Ci chondrites. And we now think that almost certainly indicates that the sulfates we see in Ci chondrites are probably formed on the Earth, interaction with water on the Earth, and have nothing to do with the parent asteroids. This is a key plot, and what this is the elemental abundances for a huge number of elements in Ryugu, what all these symbols are, divided by that in Ci chondrites. Now, if it was exactly the same as Ci chondrites, all of these points would lie exactly on the one line. What we see is that it's a very flat pattern from very, very refractory elements to very volatile elements. We also see, and this is in contrast, say, to this solid line here, which is what you see in the different type of carbonaceous chondrites, CM chondrites, which are clearly depleted in all these volatile elements. This flat pattern indicates it's a Ci chondrite-like. The fact that it lies mostly above the line is due entirely to the fact that the hydrogen and to a lesser extent the oxygen is lower in Ryugu than in Ci chondrites. And essentially this means that the Ryugu samples we've analyzed have less water incorporated into their silicates than Ci chondrites. So it's about 7% water in Ryugu and about 13% in Ibuna. Ibuna is the type meteorite for Ci chondrites. So the I is for Ibuna. And so considerably less water, and that's why you take away that, as I mentioned before, hydrogen is the second most abundant element in the rock. You take away that, everything moves up, but it's flat. And there's a lot of scatter, which is probably both due to heterogeneity in the samples, these are small samples, and analytical error, and so on. You notice tantalum is way up there, much, much, much higher than that. That's because this tantalum bullet was shot into the regolith to collect the samples, and some of those atoms were added to basically all the samples there. And tantalum is such a rare element that even that tiny bit pushes it way up. The other important thing for the rest of the talk is that the analysis showed that it's about 5% of the meteorite is carbon. The Ryugu samples is carbon, and of that, about 1.5% are carbonates, and the rest is inorganic. And this is another killer plot that shows that Ryugu is related to Ci chondrites. This is the oxygen isotope ratios. Those not familiar with these geochemical units, this is the part per 1,000 deviation of an isotope ratio from a standard. So the Earth's oceans are the standard. They sit here at 0. The value of 10 means that a sample would have 10 per mil or 1% more oxygen 17 than the Earth's ocean relative to 60. And what we can see is these different types of carbonaceous chondrites and ordinary chondrites each fall in their own place on this plot and their bulk values. We don't fully understand why that is, but it's a useful fingerprinting tool. Bulk CI chondrites here, you can see the actual data. The red and black symbols here are bulk values of Orge and Aguna, and the blue symbols are Ryugu. And again, we see a very, very good agreement between the samples and CIs, and disagreement with these other types. These other symbols are various minerals, and again, we see same result basically we see in CI chondrites. There's a very tiny difference between some of these measurements between the CI chondrites, but it needs to be confirmed. It may indicate there's some terrestrial contamination that would also explain the higher water in CI chondrites, but there aren't enough data to really tell yet. So it mostly looks like a CI chondrite from a mineralogical and chemical point of view. The one way it's different is that in some of the group, the chamber C, the second touchdown samples, we find some little class regions that are actually much less altered. And so this is a phosphoramid that's shown at LPSC, where you see these red symbols are olivine. Now, olivine you don't see in CI chondrites. It's been completely altered by reactions with water to form phyllosilicate. So this little region here has olivine and pyroxene and so on, and is quite unaltered. A paper just came out this week from Ming-Cheng Liu colleagues at UCLA, studying similar material found in a different sample from the second touchdown site. And so there's some olivine and pyroxene doing oxygen isotopes and finding some very interesting isotope variations I don't want to discuss. But the important point here is that it's clear that Ryugu is not fully aqueously altered, that on the sort of 100 micron scale, millimeter scale, there are regions that saw less alteration. And that's super interesting. This hasn't really been seen in CI chondrites, but I am sure people are now scouring their CI chondrite thin sections to look for this kind. So now I want to jump, the rest of the talk is going to talk about mainly the work I've been more directly involved in, and most of my own work has been, or all of my own work has been fundamentally doing Nanosense. Nanosense is an instrument that we can use to characterize the isotopic and elemental composition of things on very, very small submicron scales. The picture of me and the postdoc Jens Barosh, who did most of the measurements I'll be showing you, in front of the Carnegie Institution Nano Sims. There's, of course, a Nanosense here as well under the leadership of Professor Maitri Bose, and it's currently shut down, and there's construction going on and repairs going on. But once it's back up and running, people should come have a look. I think there's a lot of potential for a lot of interesting science, fairly untapped instances that can be done with this instrument. But I'm going to show you what it's useful for Ryugu. And we both used it for the IOM team, the macromolecular team, to look at the microscale distribution of hydrogen, carbon, and nitrogen isotopes, and the chemistry team to look for pre-solar grains. And I'll talk about both. So the organic macromolecule team, again, I said was led by Professor Hikaru Yabuda, who was a postdoc here with Sandra Pisarella back, and is now a professor at Hiroshima University. She led this team of about 30 or 40 people from 7 different countries. And we worked very well together, and it was a very collaborative team with samples going from one lab to another, trying to do as much coordinated analysis on the same samples as we could. Very complicated flow chart. This is not everything happened in the way it was supposed to, but this was a plan to use all these various microanalytical techniques on the samples, same samples, similar samples, to learn as much as we could about the organics. And why do we care about organic matter? Well, we know a lot about it now from carbonaceous chondrites. And we know, again, that it makes up a few percent of the meteorites. And it's a good part of the reason why the meteorites are dark. We know there's an enormous diversity of soluble organic molecules, amino acids, and various things of many are great astrobiological interest, but they only make up a small fraction of the organics. And there was a whole separate team studying those in Ryugu, and that would be a whole other talk that I can't give because I'm not on that team. But in fact, the carbon budget is dominated by this refractory sort of perogen tar coal-like macromolecule. And what we've known for some time is, one, we don't know where this stuff formed or how it formed, but it typically shows enrichments in deuterium and nitrogen-15. And both of these point to origin interesting chemistry happening at extremely low temperatures. I'm talking, tens of Kelvin that occur in molecular clouds or in the very, very outer stages of the protoplanetary disk when it's forming. And this is an example when you start looking at this at the micro scale. These are like isotope ratio maps of a bit of organic carbon extracted from the carbonaceous chondrite. And these are color coded by the deuterium hydrogen ratio and nitrogen 15 to nitrogen 14 ratio. And you can see huge variation. That's 24,000 means 25 times higher deuterium to hydrogen ratio than we see on the Earth. And so this is varying over a factor of 10 or 20 in isotope composition on a micron scale. We think these things with extremely high enrichments must have an interstellar heritage, but we don't know about the origin of everything. Some of it formed in the solar system. Is it just processed interstellar material? Does interstellar material show this wide range? We don't know. But of course, it's of great interest to understand where all these organics came from, because they're likely the first organic molecules that were on the surface of the Earth before life started forming. And we know that we can analyze this stuff by all kinds of techniques. These are the techniques that were used on carbonaceous chondrites before Hayabusa 2. We know that they're affected by parent body processing, so this aqueous alteration that clearly hydrated the silicates in Ryugu and in CI chondrites also must have affected the organic matter. You can tell this, these green points are 4 different samples of a very interesting carbonaceous chondrite called Tagish Lake. And what we found is that this rock that showed much less alteration had a higher deuterium hydrogen ratio and hydrogen to carbon ratio than the materials that were more altered. So it's clear the alteration was changing the composition. You can do infrared spectroscopy, and you can see that different meteorites have different amounts of CH2 and CH3 stretches in their aliphatic regimes. You can do transmission electron microscopy and see the morphologies, and you see that the stuff is full of these little round things that are either solid or hollow balls of carbon. These have been named nanoglobules. And some of these are isotopically anomalous, clearly predate the origin of the asteroids themselves, maybe the origin of the. You can shine X-rays through this stuff and look at how it absorbs at the edge of carbon absorption edge, carbon Zane spectroscopy. And you see these absorption features that are due to different functional groups, distinguished between aromatics, ketones, and carbonates, and all these. So you can do all of this on very, very small scales, and this was the goal for the Ryugu samples. So jumping to the initial results we have, there's a lot of this has been reported at various meetings this year. We submitted a paper in late December and revised it in May, and it's still sitting in limbo, waiting for an editorial decision on all these results. It's a little frustrating. There, rant over. This is some of the FTIR data from, this is of extracted insoluble organic matter from the Ryugu samples themselves, and you see heterogeneity, and but you see similarities and some slight differences between the CI chondrites and the Ryugu samples. It's not exactly this. This is Raman spectroscopy, which tracks the order and disorder of carbonaceous material, and you see different variations, but everything looks kind of like really unheated CI carbonaceous chondrites, like CI chondrites. The carbon Zanes has revealed a diversity of organic features, and this is showing. This is IOM, insoluble organic matter, from a couple of meteorites. Orgay is a CI chondrite. This is average IOM from the two different samples of Ryugu, two touchdown sites. And then there's also regions that look quite different, that look quite like the Murchison. But then there's other grains that look quite different, things that have mostly just show an aromatic peak, and so on. And there's far more details and many more speculative. We just wanted to give a flavor for what we're seeing. We see a huge diversity in the spectra and the chemical functionality on a micron scale, submicron scale. This is another example. One interesting thing that was found is that we find in some of these regions, we see this carbon associated with the phyllosilicates, and there's a peak at 290 EV, which is associated with CO3 groups, carbonate, but we don't see any evidence for like the features you would see in a crystalline carbonate, for example. This appears to be some sort of molecular carbonate occurring in the phyllosilicates. And this has been observed before in meteorites, it turns out, in Orgay by Le Guillou a few years ago. So now it's seen in Ryugu and is getting more attention. And now I'm going to show a few slides of work from Rhonda Stroud, who led the effort doing scanning transmission electron microscopy on this material, which really allows you to do nanometer scale mapping of the composition and functional group using X-ray spectroscopy for the elements and electron energy loss um, uh, for the functional chemistry. And she's found a huge diversity of carbon morphologies. You see that's an interesting little, like a double-walled globule, but also other fuzzy stuff or fluffy material. And there's nanodiamonds, which is also super interesting. And this is showing a diversity of the features that the STEM has shown, and in terms of different types of nanoglobules, and broken are whole, some are solid. You also see this carbon interspersed with the phyllosilicates. You also see carbon in vesicles and other minerals, and carbonate and sulfide grains. And these are almost like fluid inclusions you might find in a volcanic rock, or any other kind of rock. And which clearly, as this grain formed, it trapped some pre-existing materials, including organics, within them. These are underexplored at present, but there's a lot of more interesting to do, and so on. And this just shows again the power that's showing the diversity, what's going on here. So this is one of these nanoglobules. You can see it's got higher, that it has less nitrogen than this carbon around it. It shows up pink. Rhonda says it's a donut, or what kind of? A red velvet cake donut with strawberry frosting or something. Anyway, I think it's a Fruit Loop, but it's only half a micron across. But when you measure the spectrum, you discover this has to have aliphatic hydrocarbons in it, whereas this stuff out here doesn't. And it says distinct chemistry and functional group, less than a micron across. So super interesting. Jumping to the Nanosims, the work from my laboratory at Carnegie, what we studied some samples prepared at the Naval Research Lab that were microfilm samples on silicon wafers first. But then we got our own samples and managed to pick particles using a micromanipulator and press them into gold foils. And by we, I mean my postdoc Jens Garage did all of this. And so you end up with these nice particles pressed into gold. And we measured these with the Nanosims, measuring for their hydrogen, carbon, and nitrogen. And now I'm going to go through some of the results because they're interesting. Each symbol here, each one of these individual data points is the average of a 10 or 20 micron particle of Ryugu. What you see is there's a big scatter at the 10 or 20 micron scale in the deuterium, the hydrogen, and nitrogen 14. When you look at the average, these ellipses are 1 sigma. They're basically the average plus or minus the standard deviation of the 3 samples. Orgay was prepared and measured in the exact same way. And what we can see is that these all overlap well within 1 sigma, and so we get the same composition on average for the 2 touchdown sites and the CI content. We also see that it's enriched in deuterium. The enrichment we see at the bulk scale is in between purified organics from CI chondrites and what's measured in bulk CI chondrites. These are nominally bulk measurements, but the SIMS is more sensitive to organics, so it's not a surprise that it's out in this direction. That we're measuring a mixture of organics and water, and somehow and we see that in bulk, Ryugu is enriched similarly to CI chondrites and nitrogen 15 deuterium. But the more interesting thing is this huge amount of scatter at the 10 micron scale. That points to even more scatter at smaller scale. So now these are individual images of 2 of these particles, and this is the carbon. And just as we saw in the TEM and we saw in the SANES, the carbon is present as distinct little particles, as well as sort of fuzzier stuff in between the particles. The particles we measured are typically 300, 400 nanometers across, but they range up to 1 or 2 microns, some of the particles. And we see huge range of isotopes. So this little tiny bleb, that's probably 100 nanometers across the carbon, has a delta D value of 14,000 per mil. So it's 15 times higher deuterium hydrogen sitting right next to the stuff normal. Also in variations in nitrogen isotopes, and there's not much correlation. So that's really interesting. This is a nice, one of the first things we found is it really nicely illustrates how crazy this is. These are 4 little bits of carbon within a micron of each other, one of these samples. And this is a deuterium map and a nitrogen 15 map. And you can see there's almost no correlation. This big grain here is highly enriched in nitrogen 15 and is normal or depleted in deuterium. These 3 particles are enriched in deuterium, but this one actually is depleted in nitrogen. This is all within 1 micron. So this is extraordinarily complex stuff. And it's very hard to imagine thinking of a single organic component, for example. What are the organics of a planetary disk when they're this heterogeneous? And this is something we're scrambling to get our heads. So what I did was take all these data and do an incredible amount of tedious image processing, which is to define this individual little carbon particles in the carbon image measured along with nitrogen, carbon image measured along with hydrogen, and correlate them so we could plot hydrogen versus nitrogen together. And this is the results. What we see in terms of histograms is, first of all, we see the exact same distribution for the touchdown A, touchdown C, and Orbital. Another example that Ryugu really looks like CI. What we also see is the same thing we've seen in other carbonaceous chondrites doing similar measurements, is that most of the carbon sort of forms a Gaussian distribution around the average value, and then you have a tail of 5 to 10% of the planes have much more extreme values. We call these hot spots or cold spots if they're depletions, which are hard to see. When we plot these against each other, this is now data that I reported for some TM chondrites. I reported at the Meteoritics Society meeting last year, and some older data from the CR chondrite from MUN, and showing that there's no real correlation between deuterium and nitrogen on this half a micron scale, individual little carbon particle scale. This is the new Orgay data we got. It looks just like these other carbonaceous chondrites, and there's the Ryugu data. And the open symbols are the bulk values that I showed earlier, and these are these extreme values. What we see is that it's a very similar distribution to what we see in carbonaceous, other carbonaceous chondrites. And we get good agreement with Orgay. And there's no real correlation. So it's very hard to draw much in the way of conclusion at this point. The goal is to get a lot more information, coordinated isotope or functional group chemistry information to go along with this that might point the way to what's causing this fractionation and so on. The carbon isotopes were mostly normal in almost everything, which we've also seen, but about 2% of these regions of interest, these particles, show moderate carbon anomalies, sort of at the 200 per mil level. And again, look similar to these open symbols are literature data for carbonation. So everything we're seeing looks like what we've seen before in carbon chondrites, and there's no real correlation between carbon and hydrogen and and this is where we're hoping to head more with this. We're still working through this paper. With the hope was to do a lot more of this coordinated analysis. This is a fib section from Ryugu sample, focused on the big carbonate grain there. There's the recipe here I was showing before from Rhonda's work, but there's also little balls of carbon here, each of which was analyzed by carbon zanes, and some of them by stem eels. And then we managed to measure this in the Nano Sims for carbon and nitrogen isotopes. This is the false color map of the Nano Sims, showing that we can resolve these carbon grains. And we can calculate their carbon isotopes and their nitrogen isotopes. For one thing, we see one grain that's extremely enriched in carbon-13. That's a pre-solar grain. I'll talk about those next. But what we see is, again, the same diversity of nitrogen isotopes. But now we can plot these ratios and color code them by their spectra and start looking for trends. This is preliminary data where the color codes have to do with interpretation of the Zane spectra. This is unpublished and preliminary, and we're still working through it. It's more just to show you where we're headed for this kind of coordinated microanalysis at very small scale. So the last thing I want to talk about is pre-solar grains. In the course of measuring these carbon isotopes, we found these little hotspots with extreme carbon anomalies, and often associated with silicon. These we immediately recognized as being the presence of pre-solar silicon carbide grains that originated in stars older than the sun. Now, this is an old cartoon I made about pre-solar grains. The basic idea is that among the dust and molecular clouds are grains that form from evolved stars, supernova explosions, evolved red giant stars. These became part of the protoplanetary disk, and some of them were incorporated in primitive asteroids and meteorites, and we can extract them today. We recognize them because they have these crazy isotope ratios. So almost everything in the solar system fits within this red line on this plot, this histogram. These individual micron or submicron grains might range in carbon 12 to 13 from 1 or 2 up to 10,000. So huge range. And when you compare that to what's measured spectroscopically in stars, you can immediately make and start talking about nuclear synthesis. You can use these grains to understand how stars evolve. But you can also use the grains as probes of the early solar system, because they can be destroyed by parent body processing. And so this was exciting. We found the solar grains in Ryugu. And we then got a couple thin sections from the chemistry group to do systematic searching for pre-solar grains. And we had a paper just published a couple of weeks ago in the Journal Letters by Jens on the first results of pre-solar grains in Ryugu. So in addition to the silicon carbide, we searched for prestellar oxide grains and silicate grains, and we found 3 grains with oxygen anomalies. Again, this is a logarithmic plot of isotope ratios, and this grain here is a 200 nanometer size grain that probably formed in a red giant star. It's an aluminum oxide. This is a silicate grain, which should have been completely destroyed by aqueous alteration in Ryugu. That's probably from a supernova. We found this in that class I showed you before that was less altered, that had the olivine and pyroxene. So that's further evidence that that's less altered, and shows that Ryugu preserves some prestellar grains better than any CI compound we've seen. When we look at the abundance of silicon carbide, we get basically this average of about 25 parts per million of Ryugu is silicon carbide, and this is in perfect agreement with what we measured directly at the same time in Abuna and literature data. So again, it's a CI compound. So I'm out of time. I wanted to say there's a few, to me, some of them, there's a billion open questions on Ryugu, but to me, the most interesting ones are we still don't know why Ryugu is so dark. Got 2% albedo, darker than carbonaceous chondrites. We don't know why. We don't understand why we have such a disparity between the remote sensing infrared data and the samples. Maybe we're looking at a space weathering effect and people doing experiments to report it. And we don't understand this difference in water between CI, chondrites, and Ryugu. It might be contamination issue, but we don't know. So in conclusion, the initial analysis has revealed that that Ryugu samples are strongly related to CI chondrites. The small differences we see are likely due to terrestrial contamination, and to some extent the fact that some parts of Ryugu are less altered than CI chondrites. The organic matter is very, very diverse. So it's very much like what we see in. But we're at the very, very beginning of the analysis of these samples. There's much, much, much work. And thank you for your time.
Okay, great. Thank you, Larry. That was awesome. I want to hear more about prestellar grains. So you have to come back. Okay, so do we have questions for Larry? Sure. We have the microphone.
We actually, yeah, we'll have a mic to pass around. Nino has one. Do we have a question up?
Yeah, in the back, middle back there.
No, because it needs to go through the Zoom.
Oh, I'm sorry, I didn't get a mic to.
Right.
I'll bring it up.
I don't know what's that one. Oh, she's probably.
I have the best microphone.
Okay.
Hi, thank you for a great talk. I was just going to ask about the actual sample return itself. So I know you mentioned that it was kept in vacuum to avoid contamination with the air. Was there any preventative measure done in terms of like heating through the fall through the atmosphere, and whether that would have changed like the hydration potential or anything like that, or was it assumed to change the?
My understanding is that the design was such that it stayed cold the whole way through. That they had enough thermal shielding to keep the sample cold. I haven't heard anything to the contrary. One thing that I didn't report on because they still haven't actually reported it is in the field when they collected the canister, they hooked up a tube to a valve, and there was gas in the system that had been come out of the samples, and they ran it through a mass spectrometer, and I still don't know what they found, but but so there is more science even from the very beginning. There's the stuff degassed that we would never find in meteorite information about, but I don't know why it hasn't been published. Okay. So Rhonda Stroud said that she heard at the Meteoritical Society meeting that the outgassing stopped and they didn't have reproducible results. So that's why they're reluctant. Sciences.
Okay, another question. Yeah, the back right there.
I actually have one online here if you want to take it while we're waiting. Could the low surface hydrogen and oxygen be due to proximity of the sun during orbit, like heating?
I think that's taken into account. They understand the temperatures that are reached in general, and I don't think they're hot enough to dehydrate the sample. I think it's a few hundred Kelvin, right? I don't remember. I don't. It's not hot enough to dehydrate phyllosilicate. Good question.
Got a question up here. Thanks for the talk, first of all. I was wondering between the the Ryugo samples, between the A chamber and the C chamber, like you showed a decent amount of like chemical and isotopic data, which showed that they were pretty similar. Was there any like major noticeable physical differences that were spotted between the two? Like maybe from one coming from a lower surface layer or something?
Not to my knowledge yet, other than this discovery that some of the chamber C samples have these less altered areas, but that's also could just be a sampling bias. It might be in the chamber. But the thing to understand is it's only a tiny bit of material that's been analyzed. We don't have a measurement of either sample. So there's nothing glaringly obvious. Oh, clearly this is from below the surface, or this is completely different.
Like there's no space weathering very apparent.
There's a
on
fair
the
amount.
top?
There's a whole team. Rhonda could give a whole
I'm
talk
sure,
on
I'm
that
sure.
probably. If she is involved in that team of searching for space weathering effects. Turned out to be much more difficult than expected. Well, I don't know enough about it.
Thanks.
Next question. Zainab, down a row, maybe? No? Sorry,
Sorry.
Zainab, you'll have to wait.
I'll do another online while we're getting the microphone up. So Sydney says, what makes pre-solar stardust grains distinct from the carbon found in chondrite meteors? And how can you tell the two apart in the lab?
You can tell the two apart only if you can measure their isotopic composition. The isotope ratios of the pre-solar stardust are completely different. Factors are many different than the other carbon.
Okay, question at the back.
Hi, yeah, I was going to ask, is there any correlation between albedo and asteroid class?
Yes, yes. So some carbon C asteroids are much darker than S asteroids, which are darker than E asteroids. The M asteroids, like Psyche, are also quite dark. So it does have to do with composition, and it is thought that the reason the asteroids and carbon chondrites is dark, a big part of it is the presence of carbon. But it's not clear why Ryugu is darker than carbonaceous chondrites or other carbonaceous asteroids. It's darker than Bennu, for example, which is the asteroid that Virus Rex is. It looks very similar in a lot of ways to Ryugu, but Ryugu is darker.
Okay, could we
Nina,
get the
there was
microphone
one
to
down here.
Zainab? Zainab, wave your hand wildly so Nina knows to bring it to you. Right. And while Zainab's getting the microphone, Larry, what's next for the pre-solar grains? I'm very invested in this. I want to know.
What's next is we need to find more. So the other thing about the initial analysis team is we had to return all the samples at the end of the initial analysis period. And so we might be able to get some of our original samples back, but in the meantime, I've been allocated 2 new grains of Ryugu, and Jens has started mounting them into Sims mounts back in DC. And the hope is to find some more pre-solar grains so we can do more with them. Yes, price.
Any plans for Rhonda to maybe do 50 AM?
I would hope so.
Yeah, that'd be awesome. Okay, Zainab.
So thank you so much. That was really, really interesting. So my question is, given that they're extremely similar to CI chondrites, how do you personally think this will affect the field of meteoritics and like the direction tilting?
It's a very good question, and I don't know. I think, getting into the weeds of meteoritics, the samples could be very useful because we know they didn't interact with the Earth's environment. So we can say they're super special CI chondrites, and we can believe the data from them better than CI chondrites. But for most of the questions where that matters, it's going to be for very obscure questions. The exact abundance of some trace element. We'll have it better measured.
Thank you.
I think, like so many other things in planetary science, this is just one data point. And I think the importance of these samples are going to be shown that as an example of why sample return is so important, why we have to do so much more. And it'll be extremely important to see what the Bennu samples look like next year. As I said, it's another C-type asteroid and looks quite similar to Ryugu. If that turns out to be a CI chondrite, then that's telling us something, about the distribution of CI chondrites in the solar system. But my hope is that it's something completely different. And the best bet would be to find something we don't actually have in our sample collection, something new. We don't know. But n equals 2 is a lot better than n equals 1. And I think what we're going to learn is, in the long term, we need to get samples of 6,000 asteroids. and compare it to the 60,000 meteorites we have on the Earth.
Okay, Minnie.
Minnie has. There are no other online questions. Unless somebody wants to try to sneak one in.
Okay, so I'm going to ask you to put on your predictive hat here and say, so what is the sort of, what do you predict will be the next sort of sample return from small bodies in the solar system?
What do I predict will be, or what do I hope will be?
Either one.
My personal preference, and I think it's quite likely, would be to return a surface sample from a comet. And there is even, and there's probably at this point considered to be a continuum between really primitive bodies like Ryugu and comets. Comets have a lot of ice in them, a lot more evolved. And they're, CI chondrites are awesome because they have the same bulk chemistry of the sun, but these things at the early stages of their formation, there was ice and it melted and it reacted with everything. So you don't see a good record of what was in the disk. You see what was a good record of what it looks like when you take the stuff that was in the disk and react it with water. Comets are likely to have much less altered material, give them a much better handle on the exact start of the materials in the solar system. That's why I want comets. I think there's a good chance the next one might be from Ceres, because the Dawn mission showed that there's all kinds of very, very interesting things. Ceres, it would be a whole nother talk. I don't know, we should get a talk like that. Maybe we can. But anyway, and I would be fully supportive of that too. And this kind of goes against my answer to the other question, because of course the solar system is so diverse, you want samples of everything. And how do you get, you can't get statistics on every CE asteroid if you also want to get stuff from the comet. I don't know. We need to increase the NASA planetary science budget by a factor of 10,000. Do whatever we want.
Okay, any more questions? No?
Nothing left online.
Okay, in which case, let's thank Larry for a great talk.
Thank you very much.